All right, ladies and gents, this is 9.1, another one. This is part 3. And basically what we're going to do in this section is we're going to take a look at Taylor-Maclaurin series, and we're going to manipulate them so we can easily find another way to look at things so we can figure some things out. So that's what we're going to do. Okay, we're going to use properties of series and power series to solve complex problems, right? So we can manipulate Taylor-Maclaurin series in order to find other series by using the following techniques. One is we can substitute into a series. We can multiply or divide the series by constant or variable, okay? We can add or subtract two series, and we can differentiate or integrate a series. Okay, so let's kind of get started here with going down those specific examples. So what we want to do first is we want to find the first four non-zero terms of the Maclaurin series f of x equals sine x times cosine x. So how do we do that? Well, I want to find the first four non-zero terms. And so if I break apart this sine x here, we know that sine x from the first video in Taylor-Maclaurin series is equal to x minus x to the 3 over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial. Now remember, with sine x, the odd degrees are kept. With cosine x, the even degrees are kept. Okay, so with cosine x, we can hopefully remember that one, and that's 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial. And now, since I have the sine and the cosine both split into my four Maclaurin series, my four terms, what I'm going to do now is I'm going to multiply those together. So I'm going to take each of these individual pieces and I'm going to multiply it. Basically, you're distributing it through everything. So I'm going to show you an easy way to maybe line this up so it makes sense. So I'm going to take the x from the sine and I'm going to multiply it by the whole cosine. 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial. Now I'm going to speed this up because this is going to take a while, so I'm just going to not say anything right now. I'm just going to write what you're going to multiply it through, and then I'm going to get to this piece here and I'll explain a little bit, and then I'll speed that up too. Okay, so now I wrote it all, and hopefully you got all that, or at least paused it and did it yourself. And now I'm going to distribute everything through on all of these terms. And so now I get x, right, minus x to the 3 over 2 factorial plus x to the 5th over 4 factorial minus x to the 7 over 6 factorial. Okay, and I'm going to do the same thing for all of them. Hopefully, what you can see is if I do the next, I'm going to speed up the rest of these after this set here. But I'm going to line these up, okay? So this is actually going to be negative x to the 3rd over 3 factorial plus, and this is going to be x to the 5 over 3 factorial times 2 factorial, and that's just, that's 6 times 2 is 12. So I can start getting these factorials done. And then minus, now when I distribute by the x to the 4th, I get x to the 7 over 3 factorial 6. 6 times 24 is 144. Now, if I multiplied the x to the 3rd and x to the 6th, I get x to the 9th. But that is not part of my 4th term. That's the next set. That's the 5th term. So anything over the 4th term, which is x to the 7th or x to the 6th in this case, I'm going to stop. I'm not going to write them. So that multiplication of this times this, I am not going to write it. So what I want you to do, I'm going to speed the rest of it up, but go ahead and pause or just keep watching, and I'm going to just line the rest of my numbers up that I can actually do the math for. Go. So you can see I lined up all of my terms. I have a the x here, the 3s, the 5s, and the 7s, anything outside of those numbers will not be counted because that's not the fourth term. So now, let me add all of these up. So we get the sine of x times the cosine of x, which is what our original problem is up here. Okay, which is what our original problem is. I can add all these up, and I get is equal to x to the first minus, if I do the math here, this is really just 2, and this is 6, right? If I do that, I get minus 2x to the 3 over 6. If I do the math here, 4 factorial is 24. If I add those up, I get plus 2x to the 5th over 15. And then if I add these up, this is 6 factorial is 720. 720. 7 factorial is 5040. Everything else is good. And if I add those up, I get negative 31x to the 7 over 2520. Okay? And that, ladies and gents, is what sine x times cosine x is with the first 4 non-zero terms. There you go. I used Maclaurin series to figure that out. Let's go to the next one. All right, I want to find a Maclaurin series and the first 4 non-zero terms of f of x equals sine squared x. Well, we don't know a Maclaurin series for sine squared, or even a Taylor series for sine squared. But what do I know about sine squared? I know that sine squared x is equal to 1 minus cosine 2x over 2, right? Half angle. Okay, half angle. Well, what else do I know? I know that cosine of x, right? Traditional cosine of x, and I want to find the first terms here. I'm just going to go this way, so I get 1 minus, remember these are even, cosine's even, x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6th over 6 factorial plus x to the 8 over 8 factorial. You notice I went 5 terms, but that's okay. That's not that big of a deal right now. We're going to manipulate it and do the math anyway. All right. And the reason I guess I went with 5 because you can see that because this is going to use this a little bit, this ones are going to cancel, like this one and this one are going to cancel, and then I'm going to be left with 4, right? If you were just started with 4 when you canceled and you didn't do the x to the 8 there, then when you cancel those out, you're only going to be left with 3 terms, and so that might hinder your ability to make sure you actually get 4 terms. Okay? So now, let's figure out the rest of this. So it's 1 minus cosine of 2x over 2. Well, what does this actually mean? Cosine of 2x, that just means that wherever the x is, I just put a 2x. So this is 1 minus, right? This is 1 minus here. Parentheses, and now I'm going to add the rest of this down here. Okay? So I get 1 minus, and now it's 2x squared over 2 factorial, plus 2x to the 4 over 4 factorial, minus 2x to the 6 over 6 factorial, plus 2x to the 8 over 8 factorial. And all of that is over 2, because I'm dividing by 2. So now, my 1's are going to cancel. All right, and this becomes a positive, this is a negative, positive, and this is a negative, right? I have to multiply by that negative number, that negative 1 there. So let's see what happens now. I get 2x squared, okay, 2x squared over 2 factorial minus, let's do it this way. Let's multiply it out. I'll explain what I'm doing. So it's 2x squared minus 2x to the 4 over 4 factorial plus 2x to the 6 over 6 factorial minus 2x, all of that's to the 8 over 8 factorial. And I'm dividing that all by 2. But you can see that this 2x squared actually becomes 2 squared, which is 4x squared. And this becomes 16x squared, right? And so on. So I'm taking a 2 out of all of that and dividing it with this 2 here. So this is just 2x squared. This becomes 2 to the 3rd x to the 4. this becomes 2 to the 5, x to the 6, and this becomes 2 to the 7, x to the 8. Hopefully you can see that. Okay, that makes sense in my book. Hopefully it makes sense in your book. So this is what 1 minus cosine of 2x over 2 is equal to. Okay, that's what it's equal to. Now, this is the first 4 terms. Like, that's the first 4 terms. First 4. So that's good, because that's what sine squared x is equal to. But it says find a Maclaurin series. So now I got to find the Maclaurin series. So we're going to say sine squared of x is equal to, and a Maclaurin series involves that summation formula. So we're going to start at n equals 0 to infinity. And I want to find out, how do I get the rest of this series? Okay, how do I get the rest of this series? So I know I need a fraction. We know the denominator is always going to be what? Hopefully you realize that the denominator is always going to be even. Okay, always going to be even. So an even number is 2n. And it's a factorial, so we're going to say it's 2n factorial. The numbers as well alternate. They alternate, so I need -1 to some power. Because the first one is always positive in this case, it's going to be an n. If the first one was negative, then it would be like n minus 1, or 2n plus 1, or some version of that. Now what? Well, now I have the number 2 in all of them. So I'm going to have the number 2. But these number 2s, this is a 1, that's a 3, that's a 5, that's a 7, and so on, they're all odd numbers. So how do I get this to be a 1 with n equals 0? Well, that means that this has to be a 2n plus 1. 2n plus 1. Now what? Well, now I have x's in all of them, right? And my x's are all even. That's a 2, that's a 4, that's a 6, that's an 8. So it's got to be even, so x to the 2n. You might be thinking, well, if I made x to be 0, like, that's my denominator is going to be 0 factorial. But we know that's 1, right, from the last video or whatever. So that's 1, but my denominator here is 2 factorial. Like, that doesn't make any sense. But really, I didn't simplify it out, but isn't this really 2x squared over 2 factorial, and 2 factorial is really 2, and then the 2's can really cancel, so I'm left with just x squared. So if you actually plugged in a 0 there, you're going to get a positive 1. Okay, so it's going to be 1 times 2 times x squared. Okay, well, I had to go back and reevaluate this piece here. This is actually not correct. The reason is because you're not going to get the first couple terms. You're going to be off by a little bit. So we got to rethink on how we did this. So the -1 piece to the end, this is correct. That has to stay there because it does alternate. The 2 to the 2n plus 1, that's going to be correct as well, because it's 2 to the 2n plus 1, that's going to be odd, so I get an odd number. Like, that's going to work. If I make x 0 or n 0, 0 plus 1 is 1, right? If I make n 1, 2 plus 1 is 3, that's going to be fine. Those numbers are going to be okay. The problem is with this denominator and the x to the power. So if I made x or n to be 0, I wouldn't actually get the x squared in the first piece. Okay, that wouldn't happen. So we have to really reevaluate those numbers. And I did that over here. Okay, I spent a lot of time figuring this out just to make sure it was right, and this is what's going to happen. So this and this is going to stay the same, but the exponent here, okay, is what's going to be different. So the 2n plus 2 and the 2n plus 2, that's going to be my denominator. Those are going to have to be the same. And the reason why I did 2n plus 2 to both of them is because if n was 0, this would be x squared over 2 factorial, which is what I have here. If n was 1, this would be x to the 4 over 4 factorial, which is what I have here. If n was 2, this would be x to the 6th over 6 factorial, and that's what I have on the third term. So this is the correct answer that we should have for our Maclaurin series. So let me do this. N equals 0 to infinity, and that is our actual Maclaurin series, so not this one here that we just talked about. It's similar, so that's why we have to test. So I wrote that down, and I didn't test everything. It looks good because they're even numbers, right, and 2n plus 1 is odd, but that doesn't take into account zeros. So we got to make sure we account for zeros, and so this is the better one right there. Okay, that is that one. Let's go into the next one, which is e to the 2x, which is going to be right there. All right, find the Maclaurin series and the first four non-zero terms of f of x equals e to the 2x. Well, we can find that e to the x is equal to 1 plus x squared over 2 factorial plus x to the 3 over 3 factorial. Now, I'm not going to, I don't have to put the fifth or sixth one because I don't have any subtraction. I'm really not manipulating this too much. Well, e to the 2x is just taking all of these x's and placing them with 2x. So this is still 1 plus 2x plus 2x squared over 2 factorial plus 2x to the third over 3 factorial. Well, what does this actually mean? This is 2 squared x squared, and this is 2 to the third x to the third. Okay, so that's what basically is happening right now. This is 2 to the first, x to the first, and this is really 2 to the 0, x to the 0. Okay, over 0 factorial, and this is over 1 factorial. So now we can think about it in terms of what does the Maclaurin series look like. Okay, so I get n equals 0 to infinity. Always going to start at 0, always go to infinity. The e to the 2x is actually going to see, hopefully we can see a pattern, and it's the values 2x to the n power. Okay, if this was x equals 0, this is x equals 1, x equals 2, x equals 3. So to the 0 to the n power over n factorial, because that 0 is 0 factorial, that 1 is 1 factorial, that 2 and 3 are 2 and 3 factorials. So this is my e to the 2x expansion. If I wanted to go and do my e to the x expansion, I would get n equals 0 to infinity of just x to the n over n factorial. So the only thing that changes, you see, are so that should be 2x. The only thing that changes is this is not 2x to the n, it's just x to the n because of that 2 right down there. All right, so now let's get into the next one here, and I want to have find the first 4 non-zero terms and the Maclaurin series for e to the x plus e to the negative x over 2. Well, we can do a couple different things here. We can manipulate it in such a way that I can find the expansion of e to the x. So that's 1 plus, right, x, it's 1 plus x squared over 2 factorial plus x to the 3 over 3 factorial plus x to the 4 over 4 factorial. I'm going to go one more. X to the 5 over 5 factorial. And you might be like, well, it says first 4 and you did first 6. I understand where you're coming from when I say that, but again, stuff might cancel because I have x e to the negative x, and that's going to cancel some things. So I went a little further than maybe what I needed, but maybe I'll end up keeping the stuff that I actually wrote. If not, you just get rid of it, right? So I get e to the negative x, okay? And e to the negative x, it just changes the sign of all of my odd powers because this is negative x squared, which still remains positive. But e to the negative x to the third power, that becomes negative. And so same thing here. So this is minus x plus x squared over 2 factorial minus x to the 3 over 3 factorial plus x to the 4 over 4 factorial minus x to the 5th over 5 factorial. Okay? And so now you can see that some things are going to probably cancel, right? So if I add these up because I'm adding them right here, I actually get 1 plus 1 is 2. These are going to cancel. This becomes plus 2x squared over 2 factorial. Let's see what else. Oh, those are going to cancel. Plus 2x to the 4 over 4 factorial. The 5s are going to cancel, and actually, I probably should have went one more, right? Because x to the 6th over 6 factorial minus, oh, and that's a plus 2, x to the 6th over 6 factorial. And that's plus 2, x to the 6th over 6 factorial. So you can manipulate what you need, right? So I canceled the 3 terms out of the 6, right? And I need 4, so that's why I added that x to the 6th in. So this is what your e to the x minus, or I'm sorry, plus e to the negative x equals. But now, I got to divide that by 2 because I'm dividing it by 2. So when I divide that by 2, that actually becomes 1 plus x squared over 2 factorial plus x to the 4 over 4 factorial plus x to the 6th over 6 factorial. So this is my first 4 terms, non-zero terms for e to the x plus e to the negative x over 2. That's what I get there. Now I got to find the summation. I got to find the Maclaurin series expansion here. So I get n equals 0 to infinity of, now what's happening? Well, you can see that because these are all even numbers, technically this is like x to the 0 over 0 factorial. So what's going on? The exponent and my denominator are the same, and they're all even. So I'm going to say it's x to the 2n over 2n and then factorial. So 2n factorial. And that takes into account all of those different values there. So n is 0. That's x to the 0 over 0 factorial, which is 1. N equals 1. This is x squared over 2 factorial. N equals 2. X to the 4 over 4 factorial. And this works out all the way through. Okay, that's for that one there. Let's go to the next one. Find the first 6 non-zero terms of the Maclaurin series for e to the x plus cosine of x. So I have to break these down, right? I can say, okay, well, e to the x we know is 1 plus x, well, x, plus x squared over 2 factorial, plus x to the 3 over 3 factorial, plus, and so on, right? All the way up to however many I need. I need 6 of them, so I'm probably, let's see here, plus x to the 5 over 5 factorial, plus, now that's 6. I'm going to go a couple more. Again, it doesn't hurt to write a couple more because you might need it if stuff starts to cancel. So it might not. I'm not sure, but I'm just going to write it anyway. So we'll go to 7. Okay, we might have to go to 8 or 9. I don't know. We're going to find out. Now let's find cosine of x. Well, cosine of x is always the even degrees. So the even degrees are going to be 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6th over 6 factorial. So I'm going to leave it at that. We might have to do more, but we're going to see. Okay, so these are going to cancel. That's going to cancel. That's going to cancel. I'm sorry, this is not going to cancel. Those other 2 will. So now I add them up. So I get 2 plus x, cancel the x squareds, plus x to the 3 over 3 factorial, plus 2x to the 4 over 4 factorial, plus x to the 5 over 5 factorial. The x to the 6's are going to cancel, and then plus x to the 7 over 7 factorial. Okay? So I got the first 6 terms right there. 1, 2, 3, 4, 5, 6. So this is what e to the x plus cosine of x using the Maclaurin series. That's what it comes down to. And then I want to find the value of f prime of 0.5. Well, now I find, what do I got to do? Well, I know that if this is e to the x plus cosine of x, I need to find the derivative of this, right? This is what the expansion leads. Now I'm going to find the derivative. So f prime of x is equal to 1, this goes to 0, right, plus 3x squared over 3 factorial plus 8x to the third over 4 factorial plus 5x to the 4 over 5 factorial plus 7x to the 6th over 7 factorial. I'm going to plug in the value of 0.5. So find the derivative of 0.5. Now, I understand that you could have said, well, the derivative here, right, is e to the x minus sine x. And you could have plugged in 0.5, right? And you get e to the 0.5 minus sine of 0.5. Like, I get that. Okay, I understand that. But e to the 0.5 you really don't know the value of, and neither do you do a sine of 0.5. Okay, you don't know those values, and so because I'm using the Maclaurin series, I can then use that series to take the derivative and estimate it with fractions, and a lot easier to find the value of it. So this is 1 plus 3 times 0.5 squared over 3 factorial plus, now the rest of it, you can do the rest of it too, like you're just plugging in 0.5. And when you do that, you get around 1.169. Now, if you want to do fractions, you can do fractions too, like that's fine, but this is about what you get. Okay? Fantastic. Let's do the last one here. Use a 6th degree Maclaurin polynomial to approximate the value of sine of x squared. What is the maximum error of this approximation? So first, I got to find the expansion of sine of x squared. Well, I know sine of x is equal to, now these are the odd powers, so it's x minus x to the 3 over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial. Now, I might have to go more than that. Okay, I might have to, but we're going to be okay for right now if I do this. And so then I know sine of x squared. That means I just square everything here. So this is x squared minus x to the 6 over 3 factorial plus x to the 10 over 5 factorial minus x to the 14 over 7 factorial. Okay? The reason I went one more is because it says 6th degree, and this is the 7th degree. So I have to be higher than what it says. And because this is sine, I don't actually have a 6th degree. I have more than that. But now, what do you notice? Well, you notice that if it says 6th degree, now when I do the sine squared, I actually get a 6th degree right here. But because of the error, I have to go one more. Okay, I have to go one more. So we're going to evaluate the function from 0 to 1 of x squared minus x to the 6th over 3 factorial plus x to the 10 over 5 factorial. And all of this is dx. Let's integrate. I get x to the 3 over 3 minus x to the 7 over 3 factorial is 6. 6 times 7 is 42 plus x to the 11 over 5 factorial is 120. 120 times 11 is 1320. And that's evaluated from 0 to 1. All of this is from 0 to 1. When I do this, I get 1/3 minus 1/42 plus 1 over 1320. Minus, and then that's all 0, right? So minus 0. Because this is the error piece that I care about, I only care about, because it says what's the approximate value, I only care about this piece for the approximate value. Okay, 1/3 minus 1 over 42 is the value, and that value is something. I don't know what the heck that is. 42 minus 1 is 41. No, I'm kidding. 13 over 42. Okay, 13 over 42. And this right here is your maximum error. So your maximum error is about 1 over 1320. And thus, because we found 13 over 42, the integral from 0 to 1 of sine of x squared dx can be approximated as 13 over 42, which I believe is 0.309523. Give or take a couple decimals there, but that's about what you're going to get. So the maximum error is 1 over 1320, and then therefore the value is approximated as 13 over 42. And if you wanted to use your calculator and actually figure out the correct value, you can do that as well, but I'm not going to because we don't really need to, right? And that's it for this video. That's awesome for the maximum error and manipulation. So I guess I'll see you in the next one. Deuces.